Google would give to you. We can also say, why do we sleep? Why do we dream? This is actually 2 questions. So a normal question answering system, might not be able to do this very well, but it gives you a very good summary that answers both of these questions at the same time. And Google might be able to answer one, but it wouldn't be able to answer both. However, we still have lots of problems, and the problems are different for each task that you're trying to solve. But in particular, factuality is a big one. So I asked GPT-3, this is a little while ago, it might get it right much of the time now, but what are the largest states in the US by population and surface area? This is a somewhat difficult problem, even for people in the US to answer, but does anyone here in Japan have an idea what the answer to this would be? Yes? Alaska. Very, very good. So Alaska and California, actually California and Alaska would probably be more appropriate because you'd want to answer the question in the same question I answered, and California is the largest in population and Alaska is the largest in surface area. But GPT-3 said Alaska and Texas. And number 1, the order is wrong. Number 2, Texas isn't correct with respect to what the largest one in population is. I also asked, what is the net worth of the CEO of Twitter? And it said, Jack Dorsey is the CEO of Twitter. He is worth 2.5 billion. And this is number 1, incorrect with respect to Jack Dorsey being the CEO of Twitter. Right now, the CEO of Twitter is Elon Musk. But in a few months, it might not be Elon Musk anymore because he's apparently appointed a new CEO. The second thing is nobody other than Jack Dorsey and his accountant know how much Jack Dorsey's net worth is. It's not public information. Yet, GPT is very happy to answer these things. Other things like coherence and plausibility. I put in a prompt. This is a story about a programmer on her first day of work, and asked it to follow up. It said she was given a task to write a program that would print the numbers from 1 to 100. But for multiples of 3, print fizz instead of the number, and for multiples of 5, print buzz. This is a very standard, basic programming question that you might ask at a programming interview. But if you're asking this question to somebody by the time you've hired them, that's probably a problem, right? This is basic knowledge that every programmer should be able to do. And even worse, and then for numbers which are multiples of both 3 and 5, print fizzbuzz. Even worse, she was given a week to complete the task. She was given a week to complete the task. She was given a week to complete the task. So this is not a very plausible scenario, and the model goes in and repeats itself over and over again. And this is, this seems very simple, but nonetheless, our most powerful language models still make mistakes like this. And one of the things I'd like to argue in this talk here is that evaluating generated text is now about as hard as generating it, or maybe even more so. And the reason why is not because there's several reasons why. So the first reason why is because the text that we're generating from models is a lot better. And previously we had really poor models, and it was relatively easy to, tell when they were making mistakes, because they would make mistakes that were just completely implausible or completely disfluent or other things like this. The problem now is that language models tend to output something that looks plausible on the surface, but is actually very wrong. It might be wrong in subtle ways with respect to coherence or other things like that. It might be factually wrong, but it takes some verification to figure it out. So that makes it really tough. Another reason why it's difficult is because now, instead of handling machine translation, summarization, and question answering, which were kind of these 3 big tasks, we're now handling 100 tasks or 1,000 tasks, because language models now can handle 1,000 tasks just by prompting and asking them to do things. So we need to be able to, very quickly be able to evaluate whatever people want to do. And so in this talk, I'm going to talk about some tools that we or the community are developing in order to solve this problem. And they all fit somewhere in this pipeline of developing good NLP systems. And the first thing I'd like to talk about is how we generate results that tell you how good a generated text is in the first place. So if we look at how hard evaluation is, it varies task by task. So for classification, it's relatively easy. And when I say relatively easy, I don't mean like making a data set is easy or, figuring out exactly, your label set and the things that you want to predict is easy. But once you have a data set and a label set, it's relatively easy to tell whether it's getting the answer correct or not, because you just check whether the labels are exactly the same or not. For something like machine translation, it's quite a bit harder. And the reason why is because even if you have a translation created by a human, there are many different good translations with the same semantics. So they may not look like they overlap on the surface, but they're actually, both good translations of the output. And then if you go into harder tasks to evaluate, like dialogue, it's even more difficult because there may be many different good answers with different semantics or different meaning. So this makes it particularly tricky. And each NLP task kind of, I feel, falls on the spectrum. Maybe dialogue is one of the hardest ones. Classification is one of the easiest ones. But we can think of other things like question answering or summarization. And does anybody have an idea about where those ones would fall on the spectrum here?
There will be people who would say that all those classes are equivalent and can be, framed one through the other.
Like question answering or summarization or.
Yes, if you like in sort of your outer loop, you would say, like, if you want to do machine translation, you can wrap it into question answer and ask what would be this in English.
Yeah, that is true. And there are some places for where that makes sense. Like the places for where that makes sense are like if you're working at OpenAI or you're working at Google, building the large language models, you actually want to know how good the model is at everything. But for, I think, most practical scenarios, the great majority of people who want to use large language models are using them for a relatively specific application and not trying to build something that works for everything. So, but that is a good point.
Dialogue, maybe. It's very difficult.
Yeah, dialogue is very difficult. And then like for question answering or summarization, like where would they fit into this continuum?
I was just saying that's very difficult.
Oh, like dialogue.
Yeah.
Okay.
Like that.
I would argue that, yeah.
Harder dialogue, because there are different degrees to which you can summarize stuff. Like the idea that you make a hierarchy of importance and then you put the threshold and say, okay, I'm gonna summarize all of those that are above the threshold. But the thresholds are arbitrary, and the ranking is also arbitrary. So it's even harder than dialogue. For question answering, maybe it's between classification and translation somewhat.
Yeah, so this is a good question. I think the question answering one is, this is a little bit of a trick question with a nuanced answer like the one that you just gave. I would argue that question answering is kind of, it depends on the type you're doing. And for things like factoid question answering, where there's a clear answer, then it's between classification and translation. And the reason why is because if you said, where does Graham Neubig work? You could say Carnegie Mellon University, Carnegie Mellon, CMU. You could also say Carnegie Mellon and Inspired Cognition, which is the company I work at. So all of these would be like reasonable answers. But if you said the NARA Institute of Science and Technology, that's not true anymore. Like there is some paraphrasing, but not as much. On the other hand, if I ask you what is the meaning of life, or what is the best way to build a successful research center? These are hard questions that no human knows the correct answer to. Or the question I was asked, like, should we be training large language models right now? That's a good question. I wish I knew the answer to that myself. So yeah. And then summarization, I would argue that it's maybe less difficult than dialogue, because in general, there are clearly wrong answers where you're generating things that are not included in the original source text. So if you generate anything that's not included in the original source text, it's not a good summary. So there's a clear wrongness criterion there. So, yeah, but these are all good comments.
So in general, would you say that things that are about the future are harder to evaluate because we don't know what the future holds?
Things that are about the future, yeah, I think anything that doesn't have a clear answer, a clear objective answer is going to be hard. So if there's a clear objective right and wrong, that's going to be easier. And for translation and summarization, there's clearly wrong things to say that like have, for translation, if you drop content or add content that wasn't in the original, then that's clearly wrong. For summarization, if you add content that wasn't in the original, that's clearly wrong. So in those cases, it's a little bit easier. One interesting thing actually for subjective tasks that we're thinking about a little bit now, but I don't have any results for is, can we mimic what humans would answer for subjective tasks? So like, if you ask humans an opinion question and like 80% of people say one thing, 20% of people say another thing, the clearly wrong answer would be to say something completely different that nobody ever says, but maybe we could, mimic that subjective distribution. So I think that's interesting too. Anyway, so if we go back to kind of like what the gold standard with a question mark is, it could be manual evaluation. And in this particular case, we can ask humans we have like a source, we have two hypotheses. We can ask humans how good each of the hypotheses output by the system are, and ask them to like give a numerical answer, or ask them which one do you think is better or not. And in general, if we have skilled humans, we can trust their judgment, then this is kind of like what we would want from a actual model. The problem is this is getting harder and harder as the systems we're building are getting better and better. And actually, if we have non-careful humans or we just hire random people on Mechanical Turk, actually their judgments are not that good in the first place. So that is making evaluation harder as well, but I'm going to glaze over that for the moment and assume we have good human evaluations. So an alternative to this is automatic evaluation. And automatic evaluation, we either have a source and some hypotheses, or we have a source, a reference created by a human and some hypotheses, and we feed them into a model, and the model judges how good the outputs are. And exactly how we do this, exactly the methodology for this, I'm going to talk about some methods, but that's the general gist. So for a very long time, we were using lexical overlap metrics like blue and rouge score. And basically the way these work are we have a reference output created by a human, and we have a few hypotheses. So this is, I am giving a talk at a data science conference. I'm giving a talk at a conference about data science. And this talk is about recent advances in medical imaging. And based on this, we look at how much each of the word sequences overlap between these two. And if there's lots of overlap, we give it a high score. If there's little overlap, we give it a low score. And actually, I forgot to put this on the slide, but my favorite lexical overlap metric right now is something called CHRF, C-H-R-F. And basically the way it works is by looking at character-based, character engram-based overlap. And the reason why I like this better is because how do we define a word in Japanese in the first place, right? There's no white space, so we can't just divide on white space. Different people will argue about how you should be doing segmentation and stuff. And by just looking at character engrams, you resolve those issues and the accuracy tends to be a bit better. But anyway, lexical overlap metrics, they all look like that, but they can also be tricked relatively easily. So we have something like, I'm giving a talk at a data science conference. I'm giving a talk at a political science conference. This has lots of overlap, but it's actually a really bad output because you're getting the core information wrong. And then we also have something like my lecture will be given to the meeting on data analytics. This has little overlap, but it's a relatively good output because it essentially means the same thing. This is particularly difficult for open-ended problems like chat or other things like this, because the underlying semantics of the output could be totally different, but they could still be a good answer. So I'm going to go through a bunch of newer methods that we use to evaluate models very recently. And all of these methods essentially suddenly became much more popular starting in about 2020. And one of the reasons why it became so popular starting in 2020 is there's a very famous thing called the Conference on Machine Translation, which is one of the premier venues for evaluating evaluation metrics. So every year they have the machine translation task where they get people to build machine translation systems, but they also have the machine translation metrics task where they go in and evaluate how good metrics are for machine translation. And in 2020, they had this huge shock where basically in the machine translation metrics task, they demonstrated that all of the metrics we were using basically were decorrelated with human evaluation. If you measured correlation with human evaluation. So basically it showed that all of the automatic metrics we were using were not sufficient and we needed better metrics. So you'll notice there's a big trend upwards in terms of evaluation starting around 2020. But anyway, I'm going to talk about several segments of these. The actual metric is less important than the concept is, because all of these metrics can be updated to use newer and better models. So if I'm talking about BERT score, this is a metric that's based on BERT, but BERT's an old model, right? But we can also update the underlying model and get a better evaluation metric. So anyway, BERT score is an embedding-based evaluation metric. And the way it works is we have reference and candidate hypotheses. We feed them through an embedding model that gives you embeddings for each token in the input. And then you calculate pairwise cosine similarity between each of the embeddings. And that allows you to form a matrix of similarities between the inputs and the outputs. And then either along the rows or along the columns, you take the maximum value for each. If you're taking it along the rows correspond to tokens in the reference. So what this is doing is this is telling you how well are you recovering all of the information in the reference output. So this is essentially a recall-based metric. If you take it along the columns, this is saying of all of the things that you output, how good of a match is there? So that's a precision-based metric. It's telling you, making sure that you're not outputting any incorrect information, essentially, or information that's not entailed by the reference. Then on top of that, they also add TF-IDF weights. And basically, these are higher for rare words. And the goal of adding these weights is essentially to take care of this problem here, where you have a really important word that is wrong. So because political is much less frequent than like I or am, that would have a higher IDF weight. So it would be upweighted according to this metric. Then you take all of these, you weight them together, you calculate a value, and you can calculate the recall and precision metrics and get an F score between them. So this is nice. It's nice because it's relatively explainable. You can also get a nice visualization like this to tell you which parts look good, which parts don't look good. One other thing I'd like to point out is a lot of people just use this without thinking about it, but on their repository, they have this really nice spreadsheet of how well this does depending on the embedding model that you use. And actually, they demonstrate that by swapping in a better embedding model than BERT, namely the dBERTA model, which is a lot stronger than BERT, you can actually get a 10-point gain in the quality of the evaluation according to correlations. So it's not like you're stuck with BERT. You can use any embeddings that you want, and the better embeddings will give you better accuracy. Yeah. It's comparing it to BERT. So when I say 10-point gain, it means 10-point better correlation with human outputs. And actually, maybe I can just skip to that slide very quickly. So how do we talk about how good an evaluation metric is? Usually it's by calculating correlation with human judgments. So you assume you have some trusted good human judgments and you calculate the correlation with those. There's actually an issue with this, which is you could have something that's very correlated, but a completely different value. So actually, I think it's probably a good idea to also calculate how close it is to the human judgment in general. But anyway, correlation is what people generally use here. So the next class of evaluation metrics are trained evaluation metrics. And the way these work is essentially you have a source, a reference, and a hypothesis, and you have a human annotated output. And basically, you will take your evaluation metric, you'll predict the output, and you'll get your difference, and then you'll backprop into your metric in order to update it. So essentially what you're doing is you're doing a regression to the actual evaluation metric and trying to train a model that predicts the evaluation metric. And this is the most famous metric of this variety is something called COMET. And COMET is essentially the most popular learned metric for machine translation nowadays because it's consistently kind of been on the top of these evaluation metric leaderboards. So actually, I should probably change the title of this slide, because the maybe more important thing than the learning with pseudo data part here is learning to evaluate as question answering. And what unit eval does, what this metric here does essentially is they have a question, which is like, is this a coherent summary for the document? Or is this summary relevant to the reference? And then it puts in summary and it puts in document, and then it outputs an answer of no or yes. And this is actually a way that a lot of people are doing evaluation nowadays. A lot of people are especially using like GPT-4 to do evaluation in this way by asking it a question, a yes/no question about whether it's good or not. And so essentially what you're doing is you're taking a general purpose language model and you're just asking it, how good is this output? Unit eval in particular, I think this is a rather clever way of doing this. They're not using GPT-4, they're using an actual trained model to do this sort of evaluation. But the way they do this is they first train a kind of like strong model in general, using intermediate tasks like natural language inference, question answering, semantic, like sentiment analysis and linguistic tasks. And then they fine tune it for this evaluation using the question answering paradigm after that. And the way they create data to do this is they essentially do perturbations of good data to kind of break that good data and make it incoherent. So like to make it incoherent or incorrect or something like this. So one way you can make it incoherent is by shuffling the order of the sentences. So they take the unshuffled one is one that's coherent, and then they shuffle the order of the sentences and say this is incoherent. And so by doing this, they don't actually need annotated training data. They can just take this perturbed training data and train it this yes/no classifier. And this is a pretty strong method that a lot of people use. So another variety of models that is epitomized by BART score, which is actually something that I was a co-author on, is using the probability of a generative model to evaluate text. And the way it works is you basically calculate the conditional probability of, for example, a hypothesis given a source given a hypothesis given a reference, or a reference given a hypothesis. And the basic idea here is that you can take a generative model, and if the generative model gives a higher probability to the output, then that's likely to be a better output. If it gives a lower probability to the output, it's likely to be a worse output. And I can also go back to the original example that I gave here, which is given this output, this word political is likely to have a very low probability according to a generative model, right? Because a generative model that takes in, I am giving a talk at a data science conference, will have a lot of trouble predicting this word political because it's not entailed by the input. So that's the basic idea behind this model here, but behind this method here. And again, you could use this with any, underlying generative model. Here we use BART as a generative model, but you could also use GPT or whatever else. And then finally, one of our more recent works here combined the idea behind COMET and the idea behind BART score. And so what we did essentially was we had a generative pre-training step where we train a generative model to predict the output the probability of the output. And then we had a re-ranking step where we essentially tried to make the generative probability of hypotheses that had a better human score be higher, and hypotheses that had a better, a worse human score be lower. So you try to like upweight the hypotheses of the good outputs. And so these are some results indicating how good the outputs are. And according to correlation, one thing I should mention is that it's actually relatively hard to get good correlations here because humans themselves don't agree a lot of the time on how good outputs are. So something like a 0.4% correlation with humans is actually reasonably good. And there's a couple things that you can see here. The first thing that you can see is that compared to blue or rouge, which is on the very left side here, the learned metrics are quite significantly better. They're up to like 0.25 correlation better. So it goes from basically being nearly decorrelated with human judgment to being quite well correlated. And then finally, the metrics, the more recent metrics like unit eval and T5 score are better. I unfortunately don't have the results here for like comparing with GPT-4 or things like this, because this is a very recent trend to use these more powerful models for things like this. But I think the basic ideas still stand, which is like you can use generative models, you can use question answering based models, and all of these are like reasonable ways to evaluate generated text. Cool. So that's the first part. And after this, I want to talk about kind of like actionable ways to use these metrics in your research. Are there any questions that I could talk about for the part so far, though? Yeah.
So here, I guess the goal is also to understand, maybe evaluate how well the answer is kind of expressed.
Mhm.
The sentences are formed and grammar and
Yeah.
other things. But as you were saying, many times your goal is to think about a specific task.
Mhm.
Right? So if I think about like, writing Wikipedia entries and making some factual things right, I would go for a missing value imputation style.
Mhm.
Right? So you say capital of France is, and you would have a hole in there
Mhm.
that needs to be filled in.
Mhm.
And then it's up to the language model.
I'll go on a little bit to talk about this as well. I think that's in the next part. So I want to talk about a few other things about multi-metric evaluation, metric-aware training and inference, and fine-grained analysis. And the first thing I want to talk about is multi-dimensional evaluation of text generation tasks. And unfortunately, even despite the fact that we have all of these metrics, as I said, starting from 2020, a lot of evaluations for kind of predominant tasks like machine translation or summarization were still using the old metrics before. Especially, I created these slides originally about 6 months ago, and I think it's actually gotten a lot better since then. But this is my own paper. This is from my own paper, so you can feel free to pick on it. But even in 2022, I had trouble convincing people to use these more effective metrics. And I think the main reason why was because running evaluation was slow. It required software installation, and it was on GPU. And so I think there are a couple solutions to this. One solution is a thing that I made at the company I'm working on is it's basically an API-based evaluation metric server called Inspired Critique. If you have lots of GPUs and running on GPU is not a problem, another option is to use Hugging Face Evaluate, which basically downloads all of these things and runs them for you. And finally, since 2 or 3 months ago, there have been a lot of things that use OpenAI APIs which are expensive, but very easy to use. So I think these are all options for working on these things. One thing I want to do is I feel like it's kind of the Wild West with respect to OpenAI API-based evaluation now, and there's 17 different libraries for different ways you could evaluate, and that's not a good situation for evaluation because evaluation needs to be consistent. So one of the things I'm thinking of doing very soon is trying to unify all of these into a package that people could use as well. So I think that's one thing that we might be doing next. So I'll just glaze over that. I don't want to use too much time. So the second thing I'd like to talk about is fine-grained analysis and understanding of NLP models. And to the point right here, I think it's really important to not know just, okay, my number is 17 for this system, and my number is 17.5 for this other system. So the system that's 17.5 is obviously better, but actually having a good idea of where and how systems are working better. And one important reason why this is the case is this can go back and give you ideas for how to further improve your systems. And I kind of put this under the umbrella of NLP debugging methods. There's a lot of methods for doing this, but in particular, I would like to talk about two that I've been looking a lot at recently. The first one is fine-grained aggregate analysis, which tells us things like your model is underperforming on short sentences. And another thing is looking through individual examples, which can say, this is a potentially incorrect sentence. And then you can go in and take a look at it and form better hypotheses about why things might be going wrong. And specifically, we're building a tool to help out with this called Zeno. And the way it works is it has this example browsing interface, and it also allows you to do customizable reports. And I'm working with a student in the Human-Computer Interaction Institute in CMU. So he has this background of human-computer interaction. So it's a very it's good to interact with. I'd like to show an example of how we did this for chatbots. And so basically, what this looks like is we have a whole bunch of different chatbots here. I ran GPT-2, Llama, Alpaca, MPT, Cohere, GPT 3.5, and Vicuna, which are all these kind of recent popular chatbots. And some questions that you might want to answer are where is one model better than the other? Where is my model failing? Other things like this. Here we have BERT score and KRF is the metrics that I'm using here. So these are the ones that I talked about before. I'm just going to use KRF because it's relatively easy, or it's the default. But so here I'm looking at GPT 3.5, and GPT 3.5 obviously is very strong. It's a good, it's ChatGPT, so it's supposedly good. On the right side, I have these outputs from in insurance chat corpus. And so the insurance chat corpus essentially is simulating an insurance agent. And you can actually see here, this is the previous chat history. This is what ChatGPT output, and this is the expected output that a human operator gave. That might be a little small. I can make it a little bigger. And one of the things that you can do here is you can say, okay, where is my model failing? Where is it getting a low character F score? And so you select that, and it gives you the examples with a low character F score. And so then if we look at this, it says, yes, sir, we have different ways of confirming a customer's identity. The customer says, that's stupid. You should all be on the same page. ChatGPT says, I'm sorry, sir, can I get those numbers? And then the person says 202555. And ChatGPT says, thank you, and your social security number. But the actual answer is, expected answer is, okay, go on. And the reason why is because ChatGPT didn't know essentially that it needed to collect the whole number, the whole 12-digit customer number or something like this. That's just the first example that it found. The second example, this is at the end of a very long conversation. This one's actually pretty good. Is there damage to your vehicle? Yes, there's a dent on my front bumper and the paint scraped. Okay, do you have any injuries? Versus we'll send an adjuster to assess the damage. So asking about injuries is probably fine there. It's just semantically different, but correct.
How do you find these things?
These are just ones with low QRF score. So I just found the ones with low evaluation score. So this is a reason why evaluation metrics are important, right? Like if we have good evaluation metrics, it makes it very easy to browse potentially incorrect things, even for a strong model. Here's another example. No, that's all I think. Great. Well, thank you for calling. I hope you enjoy the rest of your day. Thank you. You as well. Thank you. This is actually wrong. The reason why it's wrong is they already said thank you, so they don't need to say it again. It might not be a big error, but it's a little bit annoying if it just keeps saying thank you to you, right? So, and then this is for ChatGPT. ChatGPT is obviously really strong and really good at kind of general purpose chat. If we go into the other ones, we can find bigger problems. Also, if we had a better evaluation metric than QRF, we might be able to focus on things where, you know, there really are fatal factuality errors or other things like that.
Do you also do like different scores give you different mistakes and then you put?
Yeah, different scores give you different mistakes. I can try to find ones with BERT score. So BERT score. Here are ones that have low BERT score. Actually, this is a similar one. This is one where the model like didn't continue with the numbers. So seems to be a pretty big model for chat, pretty big problem for ChatGPT. Let's see if I can find another one. That's another one. These are all the same problem, which is kind of, in a way, that's kind of interesting, right? I've identified a problem with our ChatGPT based chatbot and would need to go in and fix that, but I guess it's not very interesting for a demo because they're all similar. One very quick thing, other thing is you were talking about like how well does it do on different situations, you know, like and this is an example where we broke down the outputs by label length. And label length is essentially how long is the expected output. And one thing we can see is Cohere's like API-based model is actually quite good on short sentences, but on longer sentences, Cohere gets very bad very quickly. Whereas Vicuna, this open source model trained for chat, actually is still good. So you can see that like if I were working at Cohere and I were looking at these results, I would be like, oh, I have a problem with these longer outputs. I should be going in and fixing my model so that it doesn't get these embarrassing results next time, you know, they run this evaluation or something. And so, so that's another thing that this can do for you. So, but anyway, so that's one thing that we can do in order to do better, like improve models with better evaluation metrics. Then the final thing I'd like to do before I run out of time is talking about metric-aware training and inference. And I think there's two ways to improve your models through better evaluation. The first way is to get ideas about how to improve your models. So like if I had if I looked at the results here, I ran ChatGPT, I saw it wasn't appropriately handling partial numbers, I would have to maybe adjust my prompt to improve on those particular cases. But another direct way to do it is by actually taking the evaluation results and improving the training of your models. And there's a couple ways to do this. The first way to do this is by doing metric-aware training. And the way metric-aware training works is you take a metric and you try to get the model to improve the metrics that you're trying to optimize. So like, let's say I have a good metric like unit eval, and I want to train my model to do better at whatever unit eval is evaluating. We have a method that is called Brio. And the way it works is essentially, in addition to our standard maximum likelihood estimation loss that we use for always training our models, we also have a re-ranking style loss. And the way the re-ranking style loss works is it's very similar to what we did with the T5 score, which is we take the log likelihoods of two outputs and we try to re-rank the outputs so that the log likelihood of the output with a higher metric score becomes higher than the log likelihood of an output with a lower metric score. And so we try to align the log likelihoods of the generative model with the metrics. And we demonstrate that this works. This was for a while state of the art on the summarization task for CNN Daily Mail, which is kind of a big thing. That's a very competitive leaderboard. So I think that was pretty good. Recently, a lot of people have been working on RLHF, which is reinforcement learning from human feedback. It also does a very similar thing, but instead of a ranking loss, they use reinforcement learning. Then even more recently, there was a paper called RRHF, re-ranking from human feedback, which basically took our method and applied it to all of the settings where people use RLHF. And they demonstrated that this works better, essentially, than RLHF. So I can recommend this method because reinforcement learning is really painful. It's really hard to get it work. And empiric, like kind of from experience, I found that this re-ranking style method is a lot easier. A final thing, this is a method that I'd really like more people to know about. So I talk about it wherever I can go. It's something called minimum Bayes risk decoding. And the way minimum Bayes risk decoding works is essentially it's a re-ranking method that allows you to improve metric scores through re-ranking of n-best lists or other things like this. And the way it works is you output an n-best list from any model. So also one of the downsides to this method here is you need to be able to train the model. So you can't just use it with GPT-3 or something like this because you have no way to train GPT-3 using this objective. But this only requires that you're able to generate an n-best list. So from GPT-3, you could generate, 5 or 50 n-best outputs. Then you take all of the outputs and you calculate the pairwise error between them. So the pairwise error could, for example, be 1 minus your metric score. And so you get this matrix, which basically says that if my name is Bob is the correct answer, what is the error? And in this, for each of these hypotheses. And for my name is Bob, because these are the same, your error would be 0. But for all of the other ones, because this is true, this isn't true, this is not true, are all very different. From my name is Bob, your error would be very high. And then similarly, you can calculate that for all of the other kind of like gold standard hypotheses. And then for like this isn't true and this is not true, these basically have the same semantics. So the error between them would be very low. So essentially you create this matrix, then you multiply it by the probability vector that was output by your model. So maybe your model liked the hypothesis, my name is Bob, the most, but it also had the 3 other hypotheses here that it gave a reasonable probability to. And normally, if you're just doing standard generation, you would be outputting the one with the highest probability. But with minimum Bayes risk, basically what you can see is the expectation of the error, which you get by multiplying this probability by the error matrix, is lowest for this sentence here. This isn't true. And so this is what you do mechanistically, but basically the intuition is that you want outputs that are similar to all of the other outputs in the n-best list, but also have a high probability. And your similarity score is calculated according to your metrics. So if you have better metrics, you'll get a better similarity score, and you'll also get better outputs from this method. And we have a paper here called Quality Aware Decoding for Neural Machine Translation, where we demonstrate that this works for neural machine translation. But there's nothing specific to neural machine translation. Oh, and I should mention, when I say we demonstrate that it works for neural machine translation, we demonstrate that it gives better human evaluations of the outputs, not just better metric scores, which is the really important thing. So, So yeah, that's basically all I wanted to talk about today. I'll talk about the challenges and then can go back and have any discussion later. So I think there's still lots of challenges. I feel like the biggest one is right now we have essentially an arms race between like better models and evaluation metrics and human evaluation. And so we have a generative model. Better generative models equals harder evaluation. So then we need better evaluation metrics. And then ideally better evaluation metrics will lead to better generative models, either through ideas or through explicit optimization or other things like this. Another thing is automating fine-grained analysis. So I gave some examples of how fine-grained analysis can demonstrate that you're doing poorly on particular examples, but actually maybe just ignore this sentence here. What if I wanted the fine-grained analysis to tell me, oh, but you're doing poorly on examples where the speaker has spoken 4 numbers or something like that, which was actually the case for the GPT 3.5 chatbot. That wasn't included. That isn't easy to, automatically discover through any of the methods that we have here because they require like extracting features. So if we could do that automatically, that would be really cool. And then another problem is few-shot evaluation and improvement on new tasks. So like we now can do 1,000 tasks with things like GPT-4. How can we also, have a reliable evaluation metric for all of those tasks? And I don't think the answer is just ask GPT-4, because GPT-4 itself is bad at some things. It's bad at judging whether numbers are correct. It's bad at judging whether programs are correct or other things like this. So how can we very quickly ramp up to getting something that works well for, the things where GPT-4 is bad at, which is actually where we need, good evaluation in the first place. So yeah, that's what I've been thinking about a lot recently, and I'm happy to discuss more.
So, yeah, I understand that also evaluation, etc. But and also it's difficult because of the semantics and context and subjectivity, etc. So we as a NLP researcher, we are doing this. We are trying to solve these problems, and so for example, from the index model to bot and language model, it's improved. Like that. And what you are doing for evaluation is similar. You use ngram. So generation and evaluation is always like a sample. So how you can evaluate under this circumstance? Evaluation, the technological generation for evaluation is about the same status.
Yeah. Yeah, and I think the thing that is different now is how much bigger a problem this is now than it had been traditionally, specifically with respect to the difficulty in evaluating the outputs, because up until now, I think a lot of the problem was generating good evaluation data sets. And once you had a good evaluation data set generated that was representative, that answered the questions that you want to answer and other things like this, the actual verification of whether the outputs are correct or not was hard, but it was not like the problem. And I guess what I want to argue now is like, it kind of is the problem right now, in that it's just like, we don't even really know what GPT-3 can't do, or, it's like, that wasn't the case before. We knew we couldn't do machine translation. We knew we couldn't do summarization well. But I think a lot of people who aren't very familiar with evaluation, or a lot of people, we don't have a very convincing way to demonstrate that these problems aren't solved yet. And I think we're getting there. Like, I think, the work that I'm doing here, the work that other people are doing is kind of one way towards that. But yeah, that's I guess what I feel is different now.
So I understand that the quality of the problem changed.
Yeah.
From past, but that quality, that remaining problem, it cannot be solved by GPT, but also cannot be solved by evaluation.
Yeah, I think evaluation is easier than modeling once you have the methods like the ones I talked about here. And the reason why I say this is in modeling, you don't have access to a lot of the information you can have access to when you're doing evaluations. So like the most obvious example is a gold standard human output. And when you're doing evaluation, if you have access to a gold standard human output, at the very least, you can compare, semantic similarity to the gold standard human output. But I think we definitely do need to be thinking about how we can utilize all of the advances in modeling and evaluation, I guess. Because otherwise, evaluation will be falling behind modeling. Yeah, that's kind of like my argument there.
Evaluators.
Yeah.
There's no research like, or other people working on like different kind of baseline standards. There's also some situations where you don't want to mimic human.
Yeah. So I think there's lots of like pseudo. So one thing I can say is like right now there's kind of this trend, which I don't entirely agree with, of like taking GPT-4 and using it to evaluate the outputs of chatbots. And the way one way that people do this is they basically like feed in two chatbot responses and ask GPT-4 which one do you think is better. I think this has not been sufficiently validated in the same way that the methods that I like talked about here have been validated with, correlation with human responses and other things like this. I think it certainly might be a good tool, but it's kind of too early to say that. I think there's other task-specific ways that you can do this sort of evaluation. So like you can generate data sets from knowledge bases and ask knowledge-based questions. There's also the OpenAI evals that you talked about before, which is where they're having basically humans create data sets of a bunch of different. About OpenAI evals is actually it's extremely low quality. The data there. I've looked at the data and it's not very not very good.
My point was the trained force model to generate very short output to make the job easier.
Of evaluation easier, yeah.
Context can be as hard as you want, challenging different sort of things. Yeah,
Right.
it's completely made up by some people and thrown out there, but in principle, it cannot be.
Yeah.
Each sample challenging particular ability of the model to parts. So that's in that structure to understand, to challenge more knowledge,
Yeah.
to challenge vocabulary. But the evaluation is kind of short.
But so to the point, that's another method, which is like you come up with a tasks that probe things, but you make the outputs relatively easy to verify, which is, I think it's useful. Don't get me wrong, and I think there are a lot of good examples like this, like the Big Bench data set is a famous one where they like got a whole bunch of tasks that can basically be evaluated easily through simple word overlap, and they asked models to solve them. But I think one interesting thing is like when you start dealing with actual tasks that you want to solve, like chat, I am absolutely sure that nobody in OpenAI evals came up with a thing which was like, how well does ChatGPT verify the remaining digits of like social security number. It's just something you don't think of until you deal with a real situation. So I'm a pretty strong like proponent of like evaluating things in the wild in real situations like that for that reason.
Would you say that the different stages of your like model advancement, you would use different sort of evaluation methods?
Yeah, I mean, so like I've been actually surprised by how good CareF, the like simple lexical overlap based on character engrams, was able to identify even problems in ChatGPT, because ChatGPT is like a very strong model. But I think as models get better, as tasks get harder, we need stronger metrics, and you want to move away from like lexical overlap metrics. One reason why I like CareF is because it's so cheap. It's just like extremely fast to evaluate. You can evaluate it on any computer using a CPU and things like this. So if you can live with that, that's a lot better than me paying, OpenAI $50 every time I want to evaluate, a model. So.
For the context now, everybody and his friends are training big GPT-like model, and everybody's asking the same question: how do we know that our model is any good?
Yep.
And some people, oh, let's run it on glue. And some people like, come on. The people like, okay, we'll rub glue with some script to reshape it into the prompt and then automatically evaluate it this glue score or something like that.
Yeah.
So
I think there is a place for evaluating on like question answering tasks or things like this. And there was actually a really nice paper from Berkeley recently, which showed that this kind of like ask GPT-4 how good the output is style evaluation way overestimates how good some models are. It's called like on the fallacy of evaluating like imitation models or something like that. I'm paraphrasing that, and that's not the actual title, but it's something like that. And so if you ask GPT-4 how good models are, actually it says, oh, models like Llama and Vicuna and Alpaca are actually very good. But then if you evaluate them on like question answering or for factuality or other things like that, actually they're way worse than ChatGPT. And everybody knows they're way worse than ChatGPT, but it's just the evaluation that people, like the people making those models was doing, made them seem like better than they actually were. Yeah.
Maybe. Are there ways of evaluating whether the model knows what it knows and knows what it doesn't know? For example, by looking at the entropy of the output distribution.
Yeah.
Your Alaska, California example, maybe the probability of the output tokens was kind of very uniform. And then it's like too spread out. The model can say something I don't know.
Yeah. We actually have a paper called "How Can We Know When Language Models Know?" That's literally the name of the paper, and it tries to answer that question. There's a concept of calibration, and calibration is basically like if the model says it's correct 90% of the time, is it like what percentage of the time is it actually, or if the model says it has 90% confidence, is it actually correct 90% of the time, or is it correct 20% of the time? And there's something called estimated calibration error, which is basically how far off you are from that ideal, being right, the percentage of time you say. And it turns out that really strong models, if you test them appropriately, are reasonably well calibrated for simple question answering tasks, especially things like multiple choice question answering or factoid question answering, where there's like one answer. And the way you can measure that is just by, if there's only one answer, you measure the probability that the model assigns to that answer. If there's multiple choices, you measure the probability that is assigns to each choice and then normalize to get your like probability of the output. The problem is, what happens when we start doing dialogue? Now there's 10,000 ways to answer the question that all mean the same thing. It's like, what is your recommendation for evaluating language models recently? There's, not 10,000, there's a million different answers you could give to that all basically say evaluating with GPT-4 is a good idea or evaluating with GPT-4 is a bad idea, right? And in that case, measuring calibration is hard. Like it's an unsolved problem. I don't think we have a good way of doing that. I think minimum base risk is one possible way that we could start doing that, because it's basically calculating the similarity between outputs. And so if we could calculate the semantic similarity between all of those 10,000 answers that you could get out of it, then that might be one way. But I don't think there's no papers on that as far as I can tell. One other thing is like, one other thing that's interesting is I don't know if it's exactly the same, but there's like self-consistency. And self-consistency is basically measuring the how often the model outputs the same answer. And that again works for factoid question answering things. And one good thing about it is you can calculate it even if the model won't tell you the probability. So what you do is you sample like 100 outputs and you measure how often did it output like the most common answer. And if it's like 60, then it's like 60% likely. The problem is ChatGPT and GPT-4 don't give you probabilities. Like there's no way to calculate the probability of a word sequence. So the only thing you can do is like sample 100 times and see how often it output the certain things. So if you're using any other model, you can actually output probabilities and you don't have to deal with that. But like, unfortunately for ChatGPT, you have to deal with that.
Yeah,
Cool.
Last question.
Okay.
So I understand evaluation is important, but evaluation is important because generation is so bad. You know, because generation is made, I'm sorry to be attacking, but as you said, you know, people who made these tools, they made it to imitate things. It's not, the goal is not really to, you know, understand the truth or like what's being said and things and try to find the right things. So it's an imitation tool and it's mimicking the next word, right? None of the evaluation criteria that we're talking about, they are not in the model. During generation, this is not how the model is trained. So of course we shouldn't expect them to work well. And so, but still we are kind of running behind what GPT can do. We know it can do everything maybe very poorly and things that we really need. So is this driven by this arms race, this whole research, or there's some, you know, scientific things going on here?
Yeah, I would argue that that's not entirely correct anymore. And the reason why is because for two reasons. The original GPT-3 was definitely just imitating text on the internet, but now it and most of the effective models are trained using like instruction tuning or reinforcement learning from human feedback. And both of those are aimed to make the model better at the things that we do actually kind of care about. And if I go back to the example that I had here, it's even more stark if you look at the difference between Llama, which is just a language model, and Alpaca, which is an instruction-tuned language model, and Vicuna, which is a model trained specifically for chat and also including some of the reinforcement learning from human feedback. And these models are all the same base model. So like, unlike GPT-3, where we don't actually know what's going on, we actually know what's going on in these models. And you can see that like this, according to the metrics that we have here of how good it is as a chatbot, admittedly, you know, imperfect metrics, but still better than nothing. You can see a pretty stark increase. And so I think the fact that we're moving away from just imitating and moving towards like actually training the models to do the things we want is a step in the right direction. I don't think we're done. Like, I definitely don't think we're done, but I think like, you know, this loop of having evaluations that we actually care about and then methods that can go in and, you know, optimize them is a step in the right direction.
Okay, question for later.
Yeah, thanks a lot.
Exactly evaluating when or how often the model is hallucinating?
Yes. So the factuality metrics, so hallucinating is somewhat underspecified at the moment, I think. It's a term, it's kind of partly my fault because our paper was, I think, one of the first papers that used the term, but I think it's back then it was it more referred to things like summarization, where it was very clear that a hallucination meant outputting something that wasn't included in the input. But now the definition has broadened a little bit to being just any factual error, including factual errors for like open domain, like general world knowledge. And so if we just consider factual errors, there are quite a few metrics that try to measure factual errors. I think the most recent one there was a paper by like Sewon Min and other people at University of Washington that did this. I forget the name. I'm blanking on the name, but like I could find the paper for you. And we're actually hopefully going to release a paper pretty soon that does something similar. But yeah, it's definitely not a solved problem, but I think one of the interesting things is UnitEval actually does reasonably well at kind of like closed world factuality. So given an input, is the output factually consistent with input? But open world is much harder, because you need to retrieve evidence. And there, I kind of view it as a two-step process of retrieving evidence that can verify or falsify the claim, and then verifying or falsifying the claim. So closed world factuality, you're already given the evidence, and open world factuality, you also need to retrieve the evidence. So I think those are the two, axes there. Yeah.
So I have a question about Prof. Like, when you're developing these evaluations, are you kind of fearful that people who are putting out new LLMs are going to just fine tune on these evaluations themselves, artificially look good, and they're really like, the metrics would seem to be good metrics of the forming people kind of tune on these evaluations?
So number one, I want them to do that. Like, I want them to fine tune. Like, I would love for them to fine tune on the metrics, and make the metrics not useful anymore, and then we can come up with better metrics. But like, I actually have a comment about this, which is in this paper that we had here. We tried doing minimum base risk with different metrics, or re-ranking with different metrics. And specifically, we did it with two different varieties of comet. There's one variety of comet that takes in there's one variety of comet which is a referenceless metric, which takes in only the source and the hypotheses. It's called Comet QE for quality estimation. And then there's another variety of metric that takes in a reference translation. And the problem with source and hypothesis style, like reference-less evaluation, is you're basically counting on that model to be better than your generative model in the first place, because you're giving it the same information, right? Your generative model is given the source, it's generating some hypotheses. Your reference-less evaluator is also given the same amount. The ones that use references also have additional pieces of information, so they also can compare with a reference, or in the case of minimum base risk, they can compare with the other hypotheses in the n-best list and see if they're similar to the other hypotheses. So we did re-ranking with both the reference list metric and with minimum base risk using the reference metric. Re-ranking with the reference list metric caused the reference list metric to go way up, human evaluation to go way down. So basically, it exploited the metric, it found a weakness of the metric, and it failed. But re-ranking with minimum base risk worked, and it improved human evaluation and the metric itself. And so I think it's not a foregone conclusion that improving, like explicitly optimizing the metric is actually going to hurt human evaluation. So yeah, it's a very good question, and you could take a look at that paper if you want to see more.
There is one particular evaluation which is not official, quote unquote, if it makes sense, but everybody likes to do it to ChatGPT and say, hey, ChatGPT is bad. It is generate me a story about this and that in exactly 200 tokens.
Okay.
And then ChatGPT does 300 tokens and they say, hey, and it always made me think, hey, I can generate a lot of artificial examples for just this.
Yeah.
And then make them happy.
Yeah, I agree. And you could even do something simpler than that, which is like count the number of N's in the word commission, but you add like an extra N at the end and it will get the answer wrong or something. But like, yeah, that's part of the reason why I focus on evaluation for like real tasks that people care about, because, you know, who cares, right? If it gets exactly the number. However, saying it must be less than 200 characters, that's actually really important because you need less than 200 characters to fit on a mobile phone screen or something like that. You know, like demonstrating that it's wrong just to demonstrate that it's wrong is less important than, for me, than, you know, the other more practical things.
Yeah, there's a whole field called linguistics.
Yes, yes. So that's a very good question. So I feel like linguistics has been abandoned here. I have so this metric Comet, there's a reason why it's called Comet. There used to be a metric called Meteor, which was used for a while. And it's actually by the same people who created Comet. Meteor was kind of one with like manually created rules and other things like this, and it was relatively interpretable. But Comet basically just blew it out of the water with respect to performance. And so Alain Levy, who created Meteor and Comet, basically, you know, he's pursued this method because in the end it matters if it works or not. I talk to linguists all the time. I work with linguists and I work with them on particular types of problems. Like one problem where I worked with linguists a lot was on creating educational materials for very, very low resource languages. So we created like textbooks to try to help people learn Marathi or Kannada or other languages like this. And I think that's really useful because in order to teach languages humans, giving them grammatical concepts in a language that they can understand is something that would be very useful. I could be convinced to use more linguistically motivated methods for evaluation if I thought it would be improving performance with respect to the things that we care about. At the moment, I can't think of, I love linguistics. I use it for a lot of things, but I can't think of a way where it would immediately improve performance on, you know, any of the evaluations that I'm talking about here. However, I do think it might be a good way for fine-grained error analysis and like better generalizing, you know, like better finding error segments that we care about. So I think that might be a place, like maybe we're underperforming on nouns or we're underperforming on verbs. And in order to do that, we need to be able to do some sort of intelligent linguistic analysis. So, yeah.
Okay. I think this is a very good discussion.
Yeah, thanks a lot. Thanks a lot for
Thank
having
you.
me.
I think we should apologize to the people online because we completely forgot to say that they should ask questions online.
I think it can be asked. I'm happy to answer any questions for the people online. Yeah.